Here we're going to take a look at exponential modeling. Modeling is when we take a real-world situation and come up with an equation that will model that situation for us. It allows us to answer questions and solve problems. And in this video, we're going to look at models that are exponential in nature. An exponential model has an escalating rate of change. Things grow on top of growth. One way to identify an exponential model very easily is that it has a variable in the exponent. Let's look at the general form of an exponential model, and that's y equals a times b to the x. A lot of parts here, so let's see what we've got. We've got y over here is our dependent variable. X is our independent variable. Notice that independent variable that we've got in this equation is in the exponent. That's how we know we've got an exponential model. A, in this case, is our starting amount. And B is our growth or decay factor. If the situation we're working on involves growth, then it's a growth factor. If the situation we're working on involves decay, then that's a decay factor. We're going to see examples of each of those as we continue. But one thing I can tell you is it's easy to identify a growth factor because that's going to be a number that's greater than 1. And it's easy to identify a decay factor because that's going to be a number that's less than 1. Let's take a look at how we build an exponential model. The population of a town is growing at a rate of 5% per year. So what that tells me is that next year's population is going to be 105% of this year's population. So in order to find out what next year's population is going to be, I need to take this year's population and multiply by 1.05. And that comes from turning 105% into a decimal. We multiply by 1.05 to get next year's population. Now, I don't know what the current population of this particular town is, but let's call that A. So A is our current population. So after 1 year, the new population will be, well, whatever the current population is multiplied by 1.05. That would be 105% of A, which is what the population will be after 1 year. Okay, what about after 2 years? Well, let's see, A times 1.05, that's the current population times 1.05, so that's after 1 year. What I want is after 2 years. So in order to do that, it's growing 5% every year. So I'll need to multiply by 1.05 again. Just to kind of review where we're at, I've got my current population is A. And so if I want the population 1 year from now, I need that multiplied by 1.05. That's the population 1 year from now. If I want the population 2 years from now, I need to do A times 1.05, that's the population after 1 year, times 1.05 again to get me to after 2 years. And then I'm thinking you can see where this is headed now, that after 3 years, my population is going to be A times 1.05. That's 1 year. That's 2 years. That's 3 years. And I could keep this up. If I wanted the population after 20 years, I could just multiply by 1.05 20 times. And that leads us to a pattern here where After 1 year, what I've got here is a times 1.05 one time. And after 2 years, I could say that it's a times 1.05 squared. And after 3 years, it's a times 1.05 raised to the third power. So again, after 1 year, I need to multiply by that growth factor one time, raise it to the first power. After 2 years, I need to multiply that growth factor twice, so I'm raising it to the second power. After 3 years, I need to multiply by that growth factor 3 times, so I'm raising it to the third power. And that's how we build a formula for exponential growth. What our formula for exponential growth would be here is y equals my starting amount multiplied by my growth factor raised to the x power, where x is how many years down the road do you want to know about. And so there's my exponential model for this situation. Let's see how that gets used. The population of a town is growing at a rate of 5% per year. So right there, we can see that I'm going to have a growth factor of 1.05. If the current population is 6,000 people, what will the population be in 9 years? Let's see, the general form for an exponential model is a times b raised to the x. And here, what I'm trying to find is, what's the future value going to be? I know the starting value is 6,000 people. I know my growth factor is 1.05 because it's growing 5% per year. And here, x is the number of years. I was told that's 9. So really, I'm just setting up this equation that I need to simplify the right-hand side of. I just need to do 1.05 to the 9th power. And that gives me 1.551 3282. And depending on how many decimal places your calculator will hold, that may keep going. We're just going to leave that number sitting there on our calculator because we only have one more step to do. The only step left is to multiply by 6,000. And when I do that, I get 9307.969. And this is the question. The question I was asked here is, what will the population be? Well, we can't have a fraction of a person or a decimal part of a person, so we're going to round this to the nearest whole number. So we're going to find the ones place and look one space to the right. Since that number is 5 or bigger, we are going to round up. And what will the population be in 9 years? It'll be 9,308 people. And that's how we can use the growth factor to create an exponential model and then evaluate that exponential model to find out information. One more example, we're going to look at exponential decay. Where x is the number of days, a radioactive isotope disintegrates according to the function y equals a times 0.8955 raised to the x. Easy to see we have an exponential model here because we have a variable in the exponent. If there are 12 grams now, how many grams will remain after 30 days? Okay, if I'm going to use this model, I need to know the starting point, and I was given that is 12. How many will remain after 30 days? Let's see, that'll be y is equal to, there's 12 now, my decay factor, and I know this is a decay factor because it's less than 1, and because I was told that this radioactive isotope disintegrates, so it's becoming less and less radioactive over time. And this is after 30 days, so I'm going to put 30 in for x, and now we just need to evaluate the right-hand side to have our answer. The first thing we'll do is raise 0.8955 to the 30th power, and we'll get 0.03647. And we'll just leave that number sitting there on our calculator because we only have one more step, and that's multiply by 12. And when I multiply by 12, I get 0.43767. This problem told me to round to the nearest hundredth, so that's what we'll do. We'll find the hundredths place. We'll look one spot to the right. Since that number is 5 or bigger, we'll round up. And the number of grams that will remain after 30 days will be 0.44 grams.